And if you have ocean and air, well, your exposure period is really air, right? Because if I have the option of using air to replenish, right? I don't care that I can use ocean. Yes, if I use ocean, I would need more safety stock, but because I can always replenish through air, I could always assume that my exposure period is air, right? So in this case, I said, okay, let's assume that for both, I'm using the air exposure period, and I'm selecting those for the DSI policies. And then finally, it's the one that we ended up implementing, right? Because the idea with all this was to test and understand how we could come up with a policy that we could deploy, right? And you can see one of the things that I'm tracking in the simulation is this residual buildup of inventory that I mentioned, that I cannot use because I don't have a closed formula that tells me how to use it yet, but hopefully in the future I will, right? But for now, it just was information that I could use to understand how this was coming up, because I could track the average inventory position, I can track the ocean attainment, which allows me to do economic analysis and understand. I didn't put it here, but I can run on each of these what's the total fulfillment cost once I have generic costs for fulfillment of ocean and air and the inventory holding cost for the units. So when I run this, you look here, this is static because I wanted to show the curves that result from running this policy, right? So basically the attainment, the fill rate, the average inventory position, all this is the output of the simulation. And the inputs are these elements. I'm inputting forecast error, and I'm selecting the DSI targets, right? And you can see here a very interesting pattern, right? So if I look at the ocean attainment is very critical, right? Because as I mentioned, the difference for bringing a box in the ocean versus bringing it in the air, it could be, I don't know, it's a lot, right? It could be like 12 or 13 bucks per box, which is dramatically high compared to what it costs you to hold a unit and inventory for an additional day, right? When you look at the financial cost, which is the right way to look at it, right? And what you see is that when you do these policies that have the same targets, right? When you do the air only, or you do the weighted average, right? As your error goes up, your ocean attainment drops dramatically. You end up using a lot of air. So these are very, very expensive policies. Whereas when you differentiate them, right, that's when you get the higher attainment, even as the error gets bad, right? So these are much more efficient policies when you compare. Of course, you need to do the full cost analysis to determine, but you can see how they're much more efficient because the cost of this additional air is dramatic, right? So then what we said is like, okay, let me do this. I'm going to set up the ocean you to a very low resolution. So what I was saying is that, okay, so how do we come up with a strategy? I said, well, let's do the following. Because ocean has such a high impact, let's plan the ocean decision as if I was only doing ocean, right? And then what I will do is I will change these numbers manually, right? So I would run the simulation. It's basically trial and error, right? I would run the simulation shaving from the air target, right? So for example, for when you have a 10% forecast error, the formulas would have told you to run 8.6 DSI for ocean and 7.9 for air. So I start shaving that number, and I shave it across the whole curve so that every time that I run the simulation, the fill rate goes to the 95. And you can see that it's not perfect, right? You can see that on this high errors, I got it to 96 and 97, and I still decided that this was the policy because I didn't want to make it too complicated. Until I have a closed solution, it didn't make sense. I just wanted to provide a guidance. But you can see that when I did this, I ended up with very high fill rates. Whereas when I do this, depending on where I'm moving on the errors, I'm closer to the 95 that I want, right? And you can see that what's going to happen is I'm going to use much less air because I'm shaving these numbers from what I was doing before, right? Here you can see the average inventory position, right? The purple line is this policy, which is the one that I'm calling the optimal policy. And you can see that this policy is actually a policy that carries a higher average inventory position than if I did air only, right? But when you do the economics, you will see that the higher ocean utilization outweighs the higher cost of inventory that you have because you have a higher inventory position. And this is the analysis that led to finally deciding these numbers, right? I kept changing these numbers until I've managed to get this close to 95 and the economics were making sense. Once I did that, all I had to do was basically plot it and parameterize it, because I don't want to provide this whole thing to every planner. I want to provide a formula that I can code into our systems, right? We have an inventory optimizing tool that basically says, okay, this is the DSI targets based on the running forecast accuracy. And so this is basically what I need. I need a parameterized formula that I can provide. And this is this curve that you see here is basically what you would use. You would enter this formula where X is your forecast accuracy as measured by WMAP, and the output, the Y, would be your DSI target for air. Your DSI target for ocean will simply come from the traditional inventory. And that's the policy.